intelligence, analytics, data science, data warehousing, big data, anything you can think of about data, we try to bring everybody together and we try to have fun. Unfortunately, the fun part is kind of drifting away, but we're looking for ways to revive that. Our meetings are typically very casual, fun, and social. We always have some form of meal every time we meet. But we didn't want to lose touch meeting with everybody and learning. And that was why we decided to do the online presentation as well. I really want to thank Kevin. He's been very supportive and very cooperative. I've moved him from month to month, but he still made himself available this month. So Kevin, once again, thank you. I also want to appreciate our sponsors. We have Insight, we have Century One, we have Information Builders, and we typically meet in Microsoft's office. So I also want to thank them for making that available. And other sponsors, Tech Systems, CapTech, and I hope I have everybody, together in that. First, Tuesday to shift on Tuesday, but we all, and we also try to encourage people, fresh presenters. You're trying to build up your presentation skills. This is a very good way to start, and I take care of present. Please feel free to get in touch. You can send an email to Charlotte. I will give you the email address, charlottebigroup@outlook.com, or you can reach out to me on LinkedIn. My name is Moyo Lawal. I will chat that here because I know everybody will be able to spell that. So feel free. Anything regarding data, please feel free, reach out to me and I will slide you in whenever there is an available slot. For the next couple of months, we plan to have a slight change, right? Because, things are different. We can't continue to do things like we used to. So please stay tuned, watch our website, we'll send out emails or tweets, messages, and we'll let everybody, we'll carry you all along on the changes. So please tell your friends when you get to know about it, tell everybody as much as you can. It's going to be worthwhile. All right, so today, our topic today is going to be applying forensic accounting accountants and range of techniques to uncover fraudulent journal entries. And as data professionals, learning here is how to uncover dirty data. The session will about in so many use cases, outlier analysis, time series analysis, and cohort analysis. And our presenter is Kevin Feasel, and he is a Microsoft data platform. He's an MVP and the CTO at Envisage, where he specializes in data analytics with SQL and R, forcing Spark clusters to do his bidding, fighting with Kafka, and pulling rabbits out of hats on demand. He's the lead contributor to Curated SQL, and you can get that at curatedSQL.com. You can get more information from there. And he's also the author of Polybase Revealed, which is forthcoming. He's a resident of Durham, North Carolina, and he can be found cycling the trails along the triangle whenever the weather is nice enough. And I guess this is a good time to find him cycling. All right, so Kevin, thank you. And now I will hand it over to you to do your thing.
All right. Thanks. Well, thank you. Thank you so much for the introduction. One quick thing, I have had some internet troubles for the past few weeks. So if I drop off, I'll be back within a few minutes. So nobody panic and let everyone out. hopefully it'll go through smoothly. We'll be done. Everything will be great. So with that, let me share screen number. We're going to call it screen number 2. Okay, I'll call it screen number 2. So applying forensic accounting techniques. As mentioned, my name is Kevin Feasel. I am a data platform MVP, run a predictive analytics team, do quite a few things. Polybase Revealed has been released. I have to update that. But you can buy like 500 copies, and then I'll get $1 in royalties. So I think it works out. CuratedSQL.com. Every day I try to find and link to 5 to 10 interesting posts in the data platform space on topics like database administration or development, R, Python, Hadoop, Scala, Spark, Power BI, reporting services, or anything else there. So CuratedSQL.com. The concept today does have the term accounting in it, but that shouldn't scare anybody off. We're not really going to dig too deeply into accounting. I will use it as the scenario because actually I think this is a really interesting area, at least forensic accounting. So let me tell you a real story. This happened about 15 years ago. What had happened was that Wake County, where Raleigh is, their county board for transportation ended up in a bit of a problem. See, what was happening was that there was this auto parts company working in conjunction with crooked employees for the county to bilk the county and taxpayers out of money. What they were doing was that they realized if you had an invoice under a certain amount of money, only one person needed to sign off on it. Above that amount, 2 people needed to sign off on it. And so these crooked employees worked with the auto parts company who sent in a lot of bogus invoices under that cutoff. Those crooked employees signed off on it and they split the money. Now, crooked employees included actually some of the people at the top of the organization, the director of that board of transportation. Some folks served jail time. The auto parts company was found guilty and had to pay a $2.5 million criminal fine, as well as a $500,000 civil fine. And the state was able to claw back some money that was spent, that was illegally obtained for the county's purpose. So there's no exact number of quite how much money was stolen, but we know that they were able to get back about $5 million. It was pretty significant. And that led me to say, hey, this is actually a really interesting case, trying to understand how was it that they were able to get away with this fraud for years? How were they caught? And what were the tools and techniques? And as I dug into it a bit, I realized that, wait a minute, there's actually a lot of overlap with being a data platform professional, being a DBA or a database developer. And that's where I want to get into tonight. So we'll talk about actual techniques that forensic accountants do use, and we will return to this actual case a few times. The demo is a highly mocked up version of the case so that we have something we can look at. But at the end of the day, most of us are not forensic accountants. I'm definitely not. My wife actually is a CPA, but she's not a forensic accountant. So I'm not going out and trying to hunt down Bernie Madoff. But like I mentioned, these techniques actually do apply if you are a database developer. If you write SQL statements, or if you need to understand a new data model, like you're dropped into a new company and need to understand what their databases look like, these techniques do a really good job of helping you really understand your data. You may have gone to talks in the past where the presenter stands up before you and says, you need to know your data. Rarely do we as presenters go that deep into what knowing your data means. This talk tells you how to know your data. So that's what I want to give you out of this talk, that at the end of the day, this is how you can know your data. which ends up being the first agenda point. So if you have any questions at all, you're welcome to come off of mute at any point. I can't see chat, so if there are any questions, if anyone would like to shout them out for me, any time is fine. I have a few natural stopping points here, and I might actually pause to take a breath every once in a while. So we'll see about that. First up, I want to mention once again, this is all fake data. I don't have any real data. Let's call it legal liability concerns. But also, I want to call it simplification, because I want us to understand some key principles without getting lost in the details of, well, let's explain how this ERP works. Like, let's explain how this PeopleSoft implementation works. And an hour later, when we finally understand why the tables are named what they are, well, everybody goes home. So instead, I have a really simple model. A quick database model has a few tables. The key table in here is this line item table that is in the middle. And a line item is essentially an invoice that comes in for a particular bus from a particular vendor. Vendors sell items to us. The buses are our main assets. Employees work for our agency. And the combination of those, along with an expense category, the general thing that we bought, will tell you what a line item is. So expense categories briefly would be things like mirrors, seat belts, reflectors, new seats, gasoline, bus repairs, maintenance, whatever things we might spend money on to help keep these buses rolling. So we work for a company that specializes in external audits of government agencies, and we're getting parachuted into some county transportation agency. This is a brand new assignment for us, so nobody knows anything about the county so far. They haven't actually done any audits in the last several years, and we're going to come in, check out their data, and then report back to our company to see if we need to do a more thorough audit. All we have going in, they printed out this thing for us on 8.5 by 11 paper and gave you a login with some read-only access. And with that, we are going to dive deep. So let's start our deep dive with a shallow dive, some basic analysis. We're going to hit a few areas of importance early on. The first area that I want to hit is summaries. So things like row counts, data types, keys, what sort of constraints are in there. So let's talk specifically about SQL Server. And when I'm dropped into a new environment and I know nothing about the database, the sets of tables, or anything else, here's my technique for how I become familiar relatively quickly with the data. Actually, comes in Management Studio. There is a report. If you right-click on a database, reports, standard reports, disk usage by table. This gives you the just really simple data about each table. And what I'm looking for are the number of records. So the second column here gives you the number of records, and I can sort it. And what I want to do is pick the biggest, nastiest table on this list. It's like you're in prison. You go find the biggest, nastiest person and you shank them. Well, we're going to shank this line item table. And the way that we'll do that is learn as much as we can about it. So we start, we dig into this. We look at what are all the columns, what are all the keys. Hopefully this database has foreign keys. Fingers crossed that it does. It turns out that ours does, so this makes our life really easy. If it doesn't, we can look at column names, and maybe they've named the columns well enough that we can tell that, oh, this is an ID to the bus table. This is an ID to the vendor table. If that's not the case, maybe we can search in sys.columns looking for matching names and hope that they didn't make ID the name of every single table primary key. But we're going to work from this table where I've been polite, I've laid everything out appropriately, and we have some elements. You know, we know all of these keys, we know the values. We can start looking at the data, get a feeling for how much data there is, how sparse this data is, if things are nullable or not, and if they are nullable, how null are they? So is it something where half of the amounts are missing, or is it something where somebody just set it to null, but there are no null values? You know, everything is filled in. After I'm done understanding that table, I want to recursively review foreign keys. So what I mean is I've got 4 keys that I can look at here: bus, vendor, expense category, and employee. So I can look at each of these tables in turn. And when I look at the bus table, I can try to understand the columns in there, try to understand the data around it. If you're dealing with something like a warehouse, basically, we're going to find very quickly the facts dimensions and how those dimensions interplay with facts. If we're dealing with more of a transactional system, we will quickly understand the clusters of interconnected tables, which might give us an idea of, say, modules in an application or subsystems within a product. So we look at bus, we look at employee, we look at expense category and vendor. And I can also go one step further up if there are any. Say if there's a key on expense category, I'm going to say I'll recursively go through this until I understand the spidering network of interactions. Once I'm done with that, we have an enclosed set of tables, a kind of a one system. Well, let's go back, rinse and repeat. I've already looked at line item. I've looked at bus. I've looked at expense category. I've looked at vendor. I've looked at employee. Bus, employee, expense category. Yep. I have not looked at calendar or vendor expense category. So I can pick one of those, look at it, try to understand the table, understand what's going on. Now, there are a couple of exceptions where some of the biggest tables I may not necessarily care about, and I'll find out pretty quickly. Things like this is a log table, or this is a historical table, and it has there's a past data and a present data, or it's archived data, or something else that tells me very quickly that, yeah, this table is not going to be very interesting, so I can just move on to the next. But in this case, I don't really have any of those types of tables here. Calendar, if you're familiar with date dimensions, you'll see very quickly that's just a date dimension. So as we do this, if they have not given you a database diagram, if you don't have one, creating one can be useful. The tool that I use here is called SQL DBM, and it's a web-based tool. It's free for one database. There are plenty of other tools. Actually, I like Visio a lot for reverse engineering a database that doesn't change very much, because a couple clicks of mouse buttons and you're in. So there are several tools around that. If you want to get me into a rant, ask me about Management Studio's database diagrams. But for purposes of time, I will not automatically go into the rant. I have to be goaded into that one. That was taking a look at tables themselves. Once you have a feel for that, let's talk about how data has grown over time. And this is particular changes in ratios. So as we look through the data, we look at things that are amounts, are measures, things that we might want to keep track of, especially if there is a time component. So in this example, we will look at things like company growth, number of employees, revenue, cost, number of customers, amount invoiced, number of invoices. These sorts of things that we can count or sum, we'll want to track them over time and see, is there a steady growth? Are there jags upward and downward? Is it drastic change in behavior, or fairly smooth? And to do that, we're going to get started. I have right here for everybody, I'm going to bump that up just a little bit, Jupyter Notebooks running. So all of the notebooks are available. Give you a link at the end where you can grab the slides, code, and links to additional resources. And in here, I've got the first notebook, Basic Analysis. So here we are with some basic analysis. This is in the R programming language. If you are not familiar with R, don't worry, there's not too much crazy going on here, and I'll talk us through all of this. If you are very familiar with R, then don't worry, you'll still do great. Now, what I am perhaps going to do, I'll have to make sure that this works. So forgive me just one moment. Okay, cool. Wanted to make sure that Jupyter was still running. I had it opened up earlier today. Wanted to make sure that nothing was failing. So let's go through as though I didn't do that. First bit, loading a few packages. Tidyverse. The Tidyverse is an opinionated set of packages designed to get you to a concept called tidy data. Real high level of tidy data is essentially a third normal form or Boyce Codd normal form that's then denormalized to include additional columns to make analysis easier without having to do quite as many joins. So that's the real brief of it. There's a slew of packages that come with this, and I'm going to check to see if it's installed by using the require function. I'm going to install it if it's missing and load it if it's missing. ODBC lets me connect to databases. ggplot is a graphing library, so creates a set of static graphics, and we'll use that quite a few times during the course of today's talk. Now, I'm going to connect to my local host to a database called Forensic Accounting using Windows Authentication. And I'm using the DBI library to perform some queries. Essentially, give me some select statements so that I can pull in all of the data I need in order to do my analyses. So get all the data from bus, employee, from expense category, and vendor. And for vendor expense category, I'm actually going to include the vendor and expense category names so that it's clearer, so that it's not just IDs. First command in R, str, give me the structure of a data frame. When I say data frame, if you want to think of it as a table result, it's not incredibly far off. It's an okay analog. So 700 observations or rows, 3 variables, columns. And yes, I know I'm purposefully misusing the terms observations and variables, and when I compare them to rows and columns, they have more specific meanings, but for tonight's purposes, I want to keep it fairly informal. And I may just refer to them as rows and columns. So we have when the date or the bus was first brought into service and when it was retired. There were a lot of buses that we don't know when it came into service, so it was marked as January of 1990. And then there's buses that have been retired over the course of our data set. But this data was brought in as character data as opposed to date types. So we're going to use the LubraDate library to change this character data into dates. That way I can do date analysis more easily. The summary function builds out for numeric and date types a 5-number summary, which actually has 6 numbers. So the numbers that it gives you: median, 50th percentile, minimum and maximum, and then the 25th and 75th percentiles. Now R also gives you the mean, which is technically not included in a 5-number summary, but is rather useful of its own. So what we have is bus IDs 1 to 700. Dates in service, it looks like our oldest buses, we don't know when they went into service. The newest buses were brought online in 2018. Retired, there were some things that were retired in January of 2000. Looks like there are 344 buses that are not retired. They are still in service. Next thing I want to run is head to say, show me the first few buses. So this is the data. And then tell me the number of buses that have not been retired. So I can see that from here, but I can also write the calculation, get 344. So there are 700 total buses in our inventory, and 344 have not been retired. And that number probably was from an older version. So we have 344 in this case. I actually rebuilt the data set, and it's all random data, so the numbers can change. I have 12 employees. So here are my 12 employees. I know nothing about them except their first names and last names. We have 28 expense categories, and this was all of the stuff that can go wrong on a bus and need replaced. So we have a whole bunch of different things that can happen in here. We have 15 vendors, and each vendor has its own specialties. Some of them work with a lot of different components. Some of them are very specific. Like, for example, vendor 3, the only thing they do is fuel up buses. They do nothing else. They sell fuel, and that's it. Whereas a few others of these might be in working with maybe 8 or 10 of the vendor categories. So we can actually see in vendor expense categories who does what. So we have, say, vendor ID 1, they do 2 things, repair and maintenance. Come down to 3, the fuel folks, and they only sell fuel. That's it. And then there are some others who do quite a few things. So if I want to know how many things do companies normally do, well, we can use the group by function in R to say, group this by vendor ID and vendor name, and then give me the count. The in function means count. So equivalent SQL would be select count star from vendor expense categories, group by vendor ID and vendor name. And this will tell us that this company actually is involved in 12 separate categories, whereas, say, these folks are only doing 1. So we've got a fairly wide dispersion of how many things there are companies involved in. And if I look and group by expense category, we can see that there are a few sole source providers. So there's only one company that sells stop arms, crossing gates, and hatches for our county agency. There's only one that does glass windshields and windows. And that might be interesting. It might be worth discussing. Well, why is there only one? Did they sign a contract that made it so that they were going to be the sole source? Is it that there just wasn't anybody else in the county to do it? Or, that might be worthy of further investigation. But just a small note to keep. So growth analysis, how things have changed over time. And what I'm going to look at here is the number of active buses that the agency has at its disposal at different points in time over the years. So I'm going to take advantage of the fact that in this data, we retire buses on January 1st of each year. So I can look at just the year. And so what I'm going to do is take bus joined a calendar and then figure out if it's before or the year in which it was retired. And I can show this data in ggplot. So ggplot will say, graph me out something based off of my active buses result set. The x-axis will be year, y-axis will be number of buses, and we're going to have a scatter plot, so geom.point, and then we'll have a line chart also, and looks like this. We have a fairly static increase year over year in the number of active buses. So they replace buses that went out of service and then bring in new buses to enhance service. And it looks like they're really, really good at keeping this up. Not having years where you have a lot of new buses or where there are a lot that go out of service. So it's very steady. Next up, I want to say, what about invoices per year? My expectation is I would have basically a very similar relationship, because I would think coming in, okay, each bus is probably going to have about the same number of issues per year over the long run. We can make an argument that as buses get older, they'll have more issues. So as the fleet ages, maybe that changes the slope a little bit. But because we're bringing in new buses every year as well, and we're retiring old ones, that flow in and flow out maybe should even things out enough so that even if it's not exactly the same line, it should be a pretty similar line. So we'll now look at the number of invoices grouped by year, plot that as a line chart, and we see something happened. That's a fairly substantial change. That's a change of thousands more invoices than we expected. And that's a pretty big red flag for me. Now, at this point, I can tell you it looks weird. I can't tell you why or how or what it means. But I can say, I think I need to get back to that. So let's also look, we have counts of line items. Let's look at the sum of total invoiced amount by year. Cut that out. And again, that's not how these things normally work. We had fairly steady growth, although it is a little hard to tell because of the scale change. And then in 2018, it just blew up. So yeah, it looks a little suspicious. I'm kind of interested in learning more about this data to understand why we had an increase like this. And just to emphasize at this point, I'm not saying there's anything that's necessarily wrong or somebody has done something here. There might be a perfectly legitimate reason. And I'm not sure what that legitimate reason is. Maybe there was some huge run on very expensive equipment. It might make sense. But it is weird. Next, let's pivot a little bit and talk about gap analysis. So gap analysis is all about the data that isn't there. And in our world of the SQL Server database developers or BI folks, we can think of a set of problems known as gaps and islands. And there are some very smart people who have spent quite a bit of time explaining gaps and islands. And I have some links in the notes to folks like Itzik Ben-Gan or Ed Pollack, who have dedicated a lot of time to explaining this problem. So let's look at it in our data set. To do this, I'm going to need to use Python. So this talk about R will include Python because it's Jupyter Notebooks. Essentially, I'm installing PyODBC, and PyODBC simply allows me to connect to a SQL server or to any ODBC connection. I've already got it installed, and I'm loading up SQL Magic. So here I'm going to connect to an existing ODBC connection called Forensic Accounting. That is, as you would expect, pointing to localhost and the Forensic Accounting table. What this allows me to do is use %SQL to write a SQL query that will then be interpreted by Python and brought back. So here's my query. In line item, what I'm looking for are gaps in line item ID. One of the rules that you'll find in certain parts of accounting is you must have consecutive numbers. So for example, check numbers. If I give my accountant check number 1000, check 1001, and check 1003, the accountant is going to come to me and say, show me 1002. And I may say, well, what do you mean? I gave you all the checks I have. That isn't a great answer, because if check 1002 is missing, there is a possibility that maybe I tore it up. Maybe I accidentally wrote it out to the wrong person, and I tore it up and I voided it, and there's no problem here. Well, I still want to keep that check to show the accountant just to prove this thing is gone. Because what can happen is somebody with check writing authority writes a check to himself. Maybe it's for a small amount, several $100s, couple $1,000s. Company won't notice that. And cashes it and forgets to give the details to the accountant. Well, if you balance the books later, you find out that there's money missing. And then you ask, where did that come from? And that's where having these checks, having these proofs becomes really important. So we're going to look for cases where we've got missing invoices, because just like check numbers or certain other accounting numerically defined things, invoices should be sequential. We're paying people out. We'd better have the numbers, we better have these numbers right. So there shouldn't be anything missing, because we don't want to pay out something that we shouldn't have. Here's how we're going to do it. Line item. I'm looking at the current line item and using something in SQL Server 2012 and later, the lead window function. So give me the next line item ID for the ordering of line item IDs. So I'm assuming that these are monotonically increasing, and I want to just find the next line item ID. And what I'm looking for are cases where there are gaps, where the next ID is not the next number. So in this case, I have invoices 1 through 4 and 5. I don't have 6 or 7, and I have an 8. So I'm actually missing the range 6 and 7. I have a 13 and a 15, but I don't have a 14. I have 198 and 203, but I'm missing the in-between. So these are invoices that are not in our system, and that is a bit of a concern to me, because what happened to them? If they were destroyed, again, I want to see evidence that they were destroyed. Another way to do this is using a tally table. This is a technique that if you don't have SQL Server 2012, you could use this instead. Even if you have 2012, I guess you could still use it, but it is a little bit more complicated to put together. Nonetheless, it gives you the same results. It shows you the same set of line items that we just don't have in our database anymore. So one thing here, if you do generate things like invoice numbers or check numbers using SQL Server, I would recommend not using identity integers for that. And the reason is that if you have a transaction roll back, that identity integer value is gone. So you tried to insert row number 6 in, and that row failed because of a foreign key constraint violation or something. The number 6 is gone. You'll go 5 and then 7. And if an accountant looks at it, they'll say, what happened to number 6? Oh, well, I don't know. Even if you do know, you could maybe tie it back to, oh, well, there was an error when inserting into the table. That's something that really they don't like. So if you do have a situation where you have to keep track of a consecutive sequence of values, identities are not a great answer. Sequences are not a great answer. Sequences can be pre-cached, and if SQL Server restarts, well, that you move to the next set of values in the sequence. If a transaction rolls back, that session dies, the transaction rolls back, well, that sequence value is gone. So again, same key issue. If you absolutely need to build something to solve this problem, it is probably best to build it yourself, to have some sort of a serializable table that only allows one session to perform any sort of update or retrieval. Basically, you select the value, you lock the table, you're in serializable transaction isolation level. Nobody else is allowed to modify the table. You make your invoice. If that invoice succeeds, if everything commits, update the line item or next line item value table, set that number incremented, and then give up your lock on that table. Bit of a process. And if you're thinking that is going to slow things down, it will. But these typically are scenarios where you don't generally have an enormous number of invoices or an enormous number of checks. So having things slow down a bit isn't the worst thing in the world. I wouldn't do it for every table. Like if you don't need absolute guarantees of sequence values, use an identity column. It works very well as a surrogate key. You could use a sequence. It works really well as a surrogate key. But the key to surrogate keys is the values don't matter, just that they observe certain properties, like they're unique. It's when you have requirements on the specific values that this can fall apart and you may need to build your own solution. Next thing I want to talk about is regression. So we have a few things with regression. We're looking to solve a problem. We want to explain the behavior of something. Like I want to explain the behavior of total expenses. And here's what I can use to explain this. I have independent variables. These independent variables explain the dependent variable. So the thing that I'd like to learn about. And we have known data points that correlate to the values of those independent variables, as well as the value of the dependent variable, so that we can build a relationship between those independent variables that help determine what the dependent variable should be. There's quite a bit that can go on in regression analysis. We're going to stick to a very high level version. And here's a really simple regression analysis that was in the report for the accounting agency that audited Wake County. This was what they came up with. Basically, the number of buses in service versus the amount of money that was spent on maintenance. And they had essentially created a linear regression. Here is the best fit line. So given the number of buses in service, here's the amount of money that you should spend on maintenance. And it follows that line fairly well. Actually, I'd argue that there are economies of scale. So that's why they're seemingly always under the line until you get to here where something weird happened. Now, this is somewhere between like $2 and $2.5 million over the expectation. And that's a red flag. That was something that people really hadn't noticed until this audit. And that led them down the road to, well, why did that change? That year, why is that year different from other years? So let's look at it with our data set and see what we can find. All right, same libraries as before. So we're going to pop those open. Same database connection. And the data that I'm going to get, like this, some expenditure data. So we're going to find the first day of the month. And I can get that from my calendar table, my date dimension. So we're going to know what month it was. We're going to know what year it was, how many buses there were in service. We're going to know at the first day of the month, the number of invoices for that month and the sum of invoices for that month. So basically, total invoiced amount, the minimum amount was $15,000 in a month. The median is about $48,000 and the mean like $85,000. The maximum is $560,000 invoiced in a single month. So there's a fairly broad distribution here. And what I'm going to do is use a simple linear regression to say, I believe that the total amount of money invoiced is dependent on the number of buses. It goes back to my thought that you have a certain number of invoices per bus and probably about the same amount spent per bus. Again, as they get older, you spend more, but we'll see how it works out. So what do we have here? Well, we have 3 asterisks. 3 asterisks means that this is very, very important. Basically, every bus that you have adds $926.70. Your starting point is $130,000 in the hole. So it's a little bit weird to think about, but basically it adds up to, we started out with a certain number of buses. So we never had 0 buses, which is why this intercept doesn't hit 0. Okay, we explained 28% of variance. In other words, there's roughly 70% of the change in total invoice amount that we can't explain using the number of buses. There are some other factors that are important. Let's try to look at why. So this is a plot of number of buses versus total invoiced amount. And what we have is a lot of cases where like it looks about the same down here. And we have a few cases where it just skyrockets. So our model, which is trying to draw a straight line, gets a little confused near the end because there's such a big variance in a set of buses and how much money is spent per month. So, all right, that data was in 2018, because remember, we saw the huge spike in 2018. Well, let's focus on cases where our year is less than 2018. Same linear regression. Now we are explaining 87% of variance. And basically the formula is quite a bit different. Starts at $700 and then every bus adds about $190. And if we plot this, we'll see that this is the plot that I want to show. We have residuals. Residual, just fancy term for how much we were wrong. So $15,000 in one direction, $15,000 in another direction. We're wrong quite a bit. That's a fairly broad stretch, considering that our range is 15,000 to about 80,000. So we're talking 65K total split, and I can give it to you within about 60 grand. Like, yeah, that's basically saying that pick a number between 15K and 85K and you're somewhere in there. So not great, not great. Let's look at number of buses instead of expenditure amounts and number of invoices. Maybe that'll work a little bit better for us. So again, before 2018, plot the data, 94% variance explained. Essentially what this is saying is every bus generates roughly 1 invoice per month. And so that's not too bad. So I want to try to make it a little bit better. I want to say, what if we looked at calendar month? Maybe there's seasonality. School runs from these months to these months, and maybe there's a lot of work done on them in the summer, and perhaps I can take advantage of that seasonality. So we run this, and basically we go from 94% to 94%. Calendar month doesn't really change much. Okay, what about calendar year? And we saw that straight line as things grow, so maybe calendar year comes into play. We look at this. First of all, this didn't change. Still 94%. However, this changed a lot. we went from roughly 1 invoice per month with 3 stars. The 3 stars here means very significant. This is an important feature in the regression. This helps explain the dependent variable. Now, this is the amount that it helps explain it, that as the number of buses increases by 1, the estimate changes by 1.06. But this is statistically significant. We come down here, number of buses is now 0.3, and it's no longer statistically significant. Calendar year says every year add another 23 invoices. And by the way, that value is like the year 2018 will be 2018 times 23. And then in 2019, we'll add 23 more. The weird way to think about it. What's happening here is something called collinearity. And what's going on is, if I go back to the basic analysis, remember, number of buses per year increases at pretty much a constant rate. The 2 pieces of information move in the same direction at the same rate, and therefore the regression model gets confused on which one of them is doing the work, because they both behave the same way. So it's essentially arbitrarily assigning that you get some of the value, you get some of the value, and it disperses the value between them to the point where it looks like neither of these is important. But there's a 99.6% correlation between the two. And so because of that, the regression algorithm can't decide. It kind of throws up its hands and gives out some apportionment and leaves us in a situation where we don't really want to be. It doesn't give us a wrong answer, but it gives us a confused answer. And usually the solution for multicollinearity, or one solution, is take out highly correlated features. So the fact that number of expenditures and the year are really tightly correlated means I want to include one or the other, but not both. So year, I don't want to include it. It just messes up my understanding of the results. Let's take a step back, and I was looking at monthly data. Maybe I can get a better understanding with annual data instead. So again, pre-2018, my summary of annual data, number of invoices, every bus gets about 12 invoices. That explains 99% of all of the variance. There's a incredibly strong correlation here. And if I come back up, the first plot, here is the number of invoices per month. So ranging somewhere around 1,500 to 4,000. And I'm off by 50 to 60. So now we're talking about a good estimation. If I tell you it's 1,500, it's probably somewhere between, say, like 1,450 and 1,550. But that's still way better than before, where it was essentially you're in the whole range. So I would say this is a reasonably solid estimation. And if I look at the data in more detail, here is where I factor in 2018 data. So once I bring in 2018, invoices goes up from, what was it, 12? It was 1 per month for a bus and very significant, to 30 per bus and not as significant. Essentially what's happening is there was that enormous jump in 2018, and it was so bad that it really skewed our estimations considerably. So assuming that there was a problem with 2018, what should the value have been? If I come back to this line, basically what I'm asking is, assume that this is wrong, or that there's something that went wrong here. Given the pattern of history, what should it have looked like? Maybe somewhere around here. So that we can see what is the difference between the two. And that's where the predict function comes into play, because using the prior model, the one that was pre-2018, and only 2018 data, we would predict about 4,300 invoices. And in fact, we can see how we got to that, because we went roughly 300, 400 or so new invoices per year. Add about 300 and you get to 4,300. And instead we add 8,000. Again, getting back to that increase was strange. And now we can calculate just how strange it was, that we expected somewhere around 4,370 plus or minus 50, 43 to 4,400 if you want to be broad about it. That's not within that range though. That's way outside. So again, let's keep looking. Talk about cohorts. The top level aggregations that I've looked at so far can help us understand that there may be a problem, but can't help us explain what the problem is or how it was caused or what we can do about it. That's where cohorts really come into play, because we can slice the data in different ways and try to understand more based off of those slices. So a couple of ways that I want to talk about cohorts here. One is duplicates and also cardinality. So a couple angles for duplicates. You may see the same thing show up multiple times if you don't have the appropriate constraints. Maybe you have a one-time code or something that should be unique but isn't, and it's showing up multiple times. That can mess up calculations and could be perfectly innocuous, that our system had a bug and instead of inserting a row one time, we inserted it 4 times. So when you try to sum up those values, you end up with numbers that are 4 times as big. Maybe that's the case here. We can try to look into that and see. There are some other things that are close, but not quite the same. So maybe look for typos, maybe look for nearness of words to see if things ought to have been grouped together but weren't. If you want to look at grouping together of words, there are quite a few techniques. You could get into, say, natural language processing, NLP, and go hog wild in there. For techniques that are a bit more classic, Levenshtein distance or SoundX pattern matching. Some of these things are built into SQL Server, like SoundX and pattern matching. Levenshtein distance, there's a CLR method that will add that for you. There may be other techniques that you want to use to try to find word similarity. Fuzzy lookups in SSIS, for example. But it can be a huge amount of effort. Going over into NLP, again, huge amount of effort, a lot of compute power needed to solve problems of these words are near each other. Going back to the Wake County case, something that was very interesting to analysts was that there were 24 different days in which that auto parts supplier submitted 50 plus invoices, all of them under that limit where 2 people would have to sign off. So what's weird about this is that normally you would submit 1 invoice, because as soon as you submit more than 1 invoice, the people on the other side have to do more work. 2, paperwork gets lost. So there's a risk that one of those invoices may get lost in the mail and you have to resend it, may accidentally not be paid. So you may be waiting on it, may take longer to process because now you've given them a bunch of invoices. So generally, these things get batched up into as few invoices as possible. These people were sending 50 plus invoices, all of which just happen to be under this magic number, And that duplication, even if it was for different things, even if it was not truly a duplicate invoice, the fact that they were sending so many on a single day was strange. It was inexplicable. It's not normal behavior, and actually helped them understand the nature of the fraud. So let's look at our cohorts. So I'm going to pull in tidyverse and ODBC, and I have a new package as well, data table. Data table is an extremely useful package in R. Really good, great performance, and has some nice functionality built in. I will only show you a little slice of what it can do, but if you are interested in learning more about R, that's a package I highly recommend learning more about. Okay, so let's talk counts of invoices by day. Connect back to SQL Server. I want to know from line items the count of invoices per date, bus, and vendor. And I include bus in this. In our scenario, a company has to send an invoice for each specific bus. Sounds a little weird, but I wanted to include the bus as well, just to have another dimension to look at. So this is how many invoices we got for a single day for a single bus. Almost all of them are for a single, one invoice on that bus that day. There were 569 times when we got 2 invoices on the bus per day. 26 times where we got 3 invoices for that bus for the same company. So vast majority of the time, it's just 1. And I'm kind of curious about the 2s and 3s. So let's figure out who's sending us multiple invoices on a bus per day. And the way that I'm going to do that is starting off with the same set of records. So count of invoices by vendor ID, bus, and line item date. We're going to get the vendor ID and the number of times that vendor ID shows up, where the number of invoices is greater than 1. And here's what we have. These guys had 557 separate bus days where they sent in at least 2 invoices. That is an order of magnitude greater than the next highest. And all the others are in this range from about 1 to 11. And you've got 557. Seems a little weird. Seems a little weird. But maybe it's just the way that they operate. So there's nothing necessarily wrong with it. Okay. Next thing I want to do is look at the number of unique values in each column. So here's how I'm going to do it. The rapply function in R says apply this function to every column in a table or every variable in a data frame. The function I'm going to look at is the count of unique values. So there were 31,000 unique line item IDs, 460 unique buses, 15 vendors, 28 categories, 12 employees. There were 21,000 unique amounts and 2,000 unique dates. So, okay, that's cool. That doesn't tell us too much, but it gives us a feel for how dispersed certain attributes are. Like it gives us an idea that we don't have hundreds of vendors in here. We have 15. And we know that all the vendors in the vendor dimension show up in here because we had 15 there as well. But not all the buses in the bus dimension show up here, only 460. So there are some buses that never received maintenance. Okay, next thing I want to look at. Our agency has a rule where invoices under $1,000 don't need, they only need 1 signature. Over $1,000 needs 2 signatures. So we're going to look at cases where it's close to that $1,000 cutoff. And you may think that's having this sort of cutoff is absurd. But like I mentioned, that actually was the real life scenario. And another example of where you might see these cutoffs is in, say, the amount of money that you get per day for a per diem. So one of my employees, he spent quite a bit of time in the Navy back in the day. And when they would send him out to training to a conference somewhere, they would give him a per diem. It was some number of dollars per day. And the thing was that if you spent more, you could potentially get it reimbursed, but you would have to send in a receipt. If you spent, so let's say it was $10 a day. I actually think it was about $10 a day for him. So he'd get $10 a day per diem. And what he would do is go to the grocery store, spend like $2 on food, and pocket the rest of the money. And they were okay with that because if he spent $12, he could submit an invoice and get the $12 back. But now you have invoices and you have people having to do checking receipts and all kinds of process. So it was smoother for the Navy simply to say, here's $10. We're just going to look the other way as long as you don't spend more than that $10. So you see a lot less of that nowadays. Now, any reimbursement typically requires a receipt because you'd have people who would, if your per diem was $30, yes, I spent $29.99 on that. Please give me the money. And then with no receipt, okay. So receipts tend to be required. Per diems are harder to circumvent, but they still exist. So let's look at the number of unique cases for a given amount. Or excuse me, so far we haven't got the unique amount. Here's where we get some more information. So this is the set of invoices where the amount is between $850 and $1,000. So I'm calling it a high value invoice. Single person sign off, but high value. We have 2,100 of those across 12 vendors, 12 employees. Everybody signed off on those before. And if I look at the set DT, what this does is it says per vendor, how many times do they show up? Here's vendor 5 again. They show up 1,800 times. That's 2 orders of magnitude bigger than the next highest. And that's strange, but who knows? Maybe they sell I don't know, expensive windshields that are $900 a piece. And as a result, all of their invoices are that high. Maybe. So, okay, let's look at cases where it's over $1,000 by ID. You may notice a particular vendor is missing. And we've got these other vendors that are in here. And yeah, there are cases where it's an order of magnitude bigger. Here's 2 orders of magnitude difference. But we see a spread where at the low end, it's 0. And then you have the onesie, twosie types. And you've got some where you've got a few dozen, a couple where it's like just over 100. So there's a spread that feels kind of natural. But that vendor number 5 never had an invoice over $1,000. Well, how about just under $1,000? Let's say $995 or more. This is specific to vendor 5, and you can see that they have quite a few. They have 1,446 that are exactly under the limit. That's interesting. That is very interesting. It's still circumstantial. It still could have a perfectly legitimate explanation. So let's look by employee. So instead of looking by vendor, we're going to break this out by employee. What we see is that there are 4 employees who have a lot more than everybody else. So is it 4? Yeah, 3, 4. Yep. Maybe these are the senior employees. They deal with the bigger cases. Well, let's look specific to that vendor and specific to $995 or more. And specifically, it's those same people. They all handled that vendor. Okay. But maybe it's just that those people were assigned to a vendor. That, hey, okay, you get these vendors and you get these vendors and you'll fill out all of those cases. So we're going to look vendor 5 for the year 2018 by employee. We notice that everybody works on it except that these 4 people have like 2,000 cases, invoices, and everyone else has a couple dozen. By the way, 2,100 invoices over the course of 1 year means that you are getting something like 6 per day. And that's assuming that you're working every day of the year. Realistically, considering days off, holidays, and everything, it's about 7.5 invoices per day for that single company. That's a lot. That seems weird. Things are getting really weird here. So, differences, difference analysis. When we're looking at different members of a cohort, we have differences between groups and differences within a group. Between groups, we looked at this set of employees had behavior that was not the same as the other sets of employees. That can be an indicator. It could be a negative or a potential red flag, or it could just be that due to the organizational structure, we want these people to behave this way and these people to behave in a different way. So when you look within a group, especially over time, you can get a clearer picture of what's going on. Box plots are really valuable for comparing cohorts because they very quickly visualize the summary data in a way that lets you see changes rather efficiently. So this is number of invoices by month and year. Basically, the thick line in the middle is the median, 50th percentile. The box represents the 25th to 75th percentile, or the first and third quartiles, or otherwise what they're called. The topmost value represents the maximum. The bottommost value represents the minimum. Now, the lines represent 1.5 times this range from the bottom of the box to the top of the box. It's called the interquartile range from the median. So we take this size, let's say that's 10 units. Well, we would go up 15 units and we would say anything under that is normal. Anything above that is an outlier. Here's an example of an outlier. So that's how we would mark it, just as a separate dot. So we have a couple of outliers here, but everything falls in fairly standard behavior. And then in 2018, things change radically. Things fall apart. We have a huge number more invoices. But what's interesting is at the bottom end, we're still kind of in that normal area. There's some that's not necessarily weird. And then there's obviously some that's very weird. So when we're looking for these outliers, and that could be defined in the technical sense that I gave you, outside of 1.5 times the interquartile range from the median, or just in a general sense of very different, outside the norm, we can find strange behavior. Real data sets will always have outliers. It is actually strange behavior if your data set has exactly 0 outliers, because real data is imperfect. Real data is weird. So the existence of outliers is not evidence that your data is bad. It's actually evidence that your data is real. The lack of existence of outliers is an indication that your data may be phony. So let's talk about another thing when we're analyzing clustering. I talked about the cluster at $2,500 for Wake County because that was a special value. The cluster at $10 per diem because that was a special value. In our case, our cluster is $1,000. Let's come back and look at some difference analysis. Okay, tidy versus NoDBC, connect to SQL Server once more. And I'm just going to grab a whole bunch of data. Whole bunch of data from line item, expand it out, include a bunch of information about the people, about the vendors, about the expense categories. And as a gentle reminder, in case you fell asleep for a little bit and you just woke up, this is what we're trying to explain. Why did this happen? Why is 2018 so weird? And let's break it down by day, by time. So we're going to break it down by calendar month and plot data in box plots. This is the number of invoices per month and year. And you'll notice that there's a regular trend up, and then there is an explosion. But again, there's at least one point in here which is normal compared to the trend. So it's not entirely off the walls up at the top. So given that spread, let's look at number of invoices per month as just a scatter plot. So this is a value that represents a month, and this is how many invoices we had. And we actually had in 2018 at least a couple of cases that were normal, and we had a mess of abnormality. So now we're seeing, all right, these months look wrong. So let's look at the specific months. And January, November, and December look fairly normal. It was these other months starting in February going through October. February and October maybe behaves a little different. But up here, it's just crazy mode. Something happened between March and September where they just went insane in invoices. So let's look at data summarized by expense category. And what I'm showing here is expense categories by month shown as a box plot laid across in log form. And what I'm most interested in are a couple of things. One, I like to find major changes in like the width of this value. So here it ranges from effectively maybe $1 up to a couple $100. This line represents $1,000. This line represents $100. So I don't know, $200 to $400. Maybe interesting, but probably small potatoes. Up here, we've got some cases where we're looking at $100,000, but the norm is closer to 1,000. That's interesting. I want to check that out. There are a few of these where we've got outliers that are $100,000. So let's take a look at those. This is looking at expense categories by month. And this was the mean invoice amount. So here, vehicle repair labor, there's a fairly wide spread, but intuitively we can understand why there might be one. It's everything from a dent in the fender to a bus hit a tree. So yeah, I can understand. Things like exhaust, fairly big spread. Glass windshields and windows, there's some huge outliers. So I'm kind of interested in those outliers. So what I'm doing in here is looking for extreme outliers in a direction that's interesting. The ones that are closer to zero, I'm a lot less interested in. The ones that are further away, I'm more interested in. And since I talked about glass windshields and windows a couple of times, let's find out who sells in that category. These guys. By the way, these guys, their vendor ID is 5, just in case that wasn't clear yet. So they have this weird distribution where there's this huge number of outliers and the median is just under $1,000, $999.99, or thereabout. But there's this huge number of lower values. And by the way, there's nothing that ever goes above $1,000 because these guys never had an invoice of 1,000. All right. This company sells 4 different categories of things. So we want to see what the competition looks like for those categories. I'm going to start before 2018 because we know before 2018 it looked kind of normal. And here's what it is. For glass windshields and windows, they're a sole source provider. They were the only ones who sold. Lights and reflectors, looks like they're competitive. Mirrors, they're competitive. They're selling about the same price. Windshield wipers and parts, selling about the same price. And the size of the box plot here, I have a setting here, variable width. So the size of the box plot actually represents the number of times a value shows up. So that becomes important when we look at the 2018 data. 2018 data, that changed. Here, they became much more expensive. That solid black line is past this one. And yet the box is bigger. The county agency spent more money, had more invoices for the more expensive company. Same thing with mirrors, same thing with windshield wipers and parts. In every one of these cases, they became considerably more expensive and had a lot more number of invoices coming in. So that's very weird behavior. Not at all normal. Now, I don't have anything yet, but let's talk about employees. Maybe we can learn a little bit more and start to piece things together. So this is a box plot of amounts per employee overall. And if you see nothing interesting in here, then you're probably about right. I mean, I see that there are some people who have high-end ranges, but I'm looking at this and saying, I don't see anything weird. So let's focus on pre-2018 data, specifically for vendor 5, because I'm already suspicious about this company. So pre-2018, I see nothing weird here. There's a spread of data. Spread of data looks all right. In 2018, this is no longer a spread of data that looks all right. This is radically different behavior where these 4 people have dealt with plenty more invoices. These are the 4 people that had 6 or 7 invoices per day in 2018, and the average invoice amount jumped considerably from what we were dealing with before. So those 4 people are handling all of those invoices. Now, let's go a bit further. We're going to look at the normal months and the weird months. In the normal months, here's behavior. There's separation, there's splitting, but nothing to the eye that looks really weird. I mean, like she has a few more invoices than some of these other people, but her median is not that bad. It's, actually lower than several of these folks. The weird months. Those 4 people all have roughly the same behavior through that range and are radically different than everybody else. In the same months where that one agency was submitting a lot of invoices that happen to be just underneath the cutoff. So there might be a valid explanation for this. I mean, this is not, I'm going to throw you in jail because of this. But it is, now it's time to start auditing each one of those invoices, understanding what the parts were and trying to get receipts of parts and pictures of things. This is where the actual forensic accountants come in and spend 3 or 4 months putting together a case and understanding exactly what went on. Last thing I want to show on this clustering behavior is around that $1,000 mark. This is for customer 5. And you hit a wall at $1,000. And there's actually, this is for everybody, all customers. So you hit that wall at $1,000 and there's a bit of trickle beyond. Here's vendor 5. They hit the wall. They never go beyond the wall. Here's everybody else. There is no wall. So this is the only company that has a wall at $1,000. Again, very weird behavior. This is, at this point, this is the type of information I could put together in a report, give to people who would look at the books, and let them run wild on it. Last couple of things I want to touch on as we wrap up for tonight. First is numerals. So I will skip past time series because we actually kind of talked about time series in this. You can get an idea of behavior of a data set based on the round numbers. So grouped by the number of ending zeros, ignoring decimal points. So like $5,000 has 3 zeros at the end. 10,200 has 2 zeros at the end. So the fact that there's a 0 here doesn't matter because it's after the last non-zero digit. And in a normal data set, what you would expect to see is a uniform distribution of the last digit most of the time. So what I mean by that is you are just as likely to find a 0 as you are to find a 4, as a 7, as a 9. Was there a question? Oh, okay, cool. So you're just as likely to find any one of those values. There are exceptions to this. An exception is budgets. Budgets almost always have numbers that end in 0. So that you would not expect a uniform distribution of the last digit. Here's my data set. And percent of type 0 by category. So what I mean by type 0 is you end in a number between 1 and 9. Notice that about 90% of these, except for these weirdos, 90% of these end with the numbers 1 through 9. That's consistent with a uniform distribution. Roughly 10% of your values end in 0. Now, the second to last digit, basically every digit after the first, you assume is uniform. And what you would expect is that you have about an order of magnitude drop off for each. So 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. And that's what we're seeing here, where the numbers naturally drop off and you have orders of magnitude falling. These folks even exhibit it a little bit until you get to this part where they had 1,448 in the type 3. That's because they had $999.99, and I ended up rounding that up to $1,000. So that was another case where I got to see your behavior is very different from all of your peers. Worthy of investigation. If I look at this data across all vendors, again, we can see 5, 4, 3. I would expect to see about maybe 50 in this area, not 1,400. So that's a red flag. And we can see that this is all because these guys are very obviously gaming the system. So that's last digits. Last digits we assume are uniform. They're going to have a flat distribution. First digits actually follow a totally different rule called Benford's law. So in many data sets, natural data sets, artificially generated data sets, you will find that the first digit about 30% of the time is the number 1, and then about 18% of the time is the number 2, and so on down to 9%, or Actually, the number 9 is less than 5% of the time.
Okay, looks like we lost Kevin briefly. Like you said earlier, he's going to connect back. So let's give him a few minutes and then we'll wrap up. Thank you. Okay, so while we kind of give him a few more seconds just to see if we can log in and wrap up. I know it's time and I really appreciate your patience. Does anybody have any question about CBIG or anything that you'd like to comment on? Okay, Kevin is joining. I know someone was trying to unmute himself. You can go ahead and ask or speak.
Yeah, this is Shubham. I just wanted to thank you guys. This was my first meeting related to Charlotte BI. I really liked it. I enjoyed all the Kevin's presentation. So just wanted to thanks and looking forward to future meetings as well. Thank you so much.
Thank you so much, Shubham. I really appreciate the feedback, and I'm glad you learned a lot today, just like I did. I took some notes.
Yeah, this will definitely help me in my job.
Okay.
Sorry about that. That thing I mentioned happened where my internet turns into a pumpkin at midnight.
Yes. And almost everybody waited. So thanks, guys. I'll hand it back to you, Kevin, to wrap up now.
Okay. So I was
Thanks, Kevin.
talking about Benford's law, and let's see if I can share my screen. That's the screen I want to share. I'm not sure exactly where I got cut off. Did I get to the point where I was explaining North Carolina populations?
I guess that was where you're going to start. Could you go up a bit? Let me see.
Yep.
Yeah.
Okay, so I'll just walk through Benford's law once again. Brief concept. First digit behaves rather differently from last digits. Last digits we assumed were flat, that 1s and 2s and 4s and 8s were just as common as everything else. Here, the behavior is really different. 1s come up a lot more often than 9s. And there's a logarithmic curve around how these values show up. Actually, the guy who discovered this was looking at logarithmic tables when he made the discovery. This phenomenon shows up in a lot of natural data sets. So I'm going to show you a couple of those natural data sets. And one of them is population of cities in North Carolina. This was as of 2013. So we have, like, Charlotte has 800,000, so 8. Raleigh, 440,000, 4. 2, 2, 2. If I run this, my bar chart here, the histogram, is the percentage of values that start with that digit. So the line represents the perfect Benford curve. Roughly 27, 28% of cities in North Carolina in the year 2013 had their population start with a 1. Their digits start with a 1. And we can see that it's not an exact match, but it is actually really close. Here's another example. Actually, so here it is looking at it in a tool called Benford.analysis. It's a package in R that lets you see a lot of really cool information and give you some specific details about what would be a perfect Benford curve of fit and how your data is different. So mean of 0.5, variance of 1 over 12, kurtosis of -1.2, and 0 skewness. If you have all of those attributes, then your data follows a perfect Benford curve. In this case, our mean is just over 0.5. Our variance is just a little low. Kurtosis a little low, skewness a little low. So it's not perfect. Really close. Here's our expenses data. If I look at our Benford plot, it is reasonably good until we get to the 9s. Remember, all those bogus $999 invoices, they pushed our value, our frequency, up significantly. Most of these other things were following the Benford curve. So if you see something that quite a bit different in this curve, it may be an indicator to dig a little deeper. Here's how it looked prior to 2018. Prior to 2018, it looked like an exact Benford curve. And that's why when I look at that 2018 data and say, something went on here, that's not right. There are quite a few other cases where you'll find that the Benford analysis fits. Population is a natural example. Square footage of houses actually fits that example. Square acreage of houses, of properties, square miles of city parks. There are a lot of things that just happen, and the data sets fit pretty well to a Benford curve. But last digits, again, are flat. This is North Carolina populations, and the percentages they range somewhere between 0, say 8% and about 12%. Our expense data, we had some extra zeros, admittedly, but that's not too weird. Actually, some of that was the fraud. And the rest of this is pretty flat. First digits follow that logarithmic drop. Last digits generally flat. Prior to the last digit, or after the first digit, generally pretty flat. There are exceptions. And if you know you're in an exception, throw that rule out. Budgets are an exception. That last digit will almost never be anything other than a 0 unless you know exactly the dollar amount you're budgeting to. So this has been quick, maybe aspirational of a term, but it's been a survey of forensic accounting and outlier detection techniques. We've covered a lot tonight. You can apply these techniques to your data sets. This doesn't have to be for fraud. This can just be for really understanding the relationships in your data and getting a good feeling for how things fit together and how your data changes over time. If you want to learn more, grab the slides, the demos, links to additional resources. That is all at csmore.info/on/outliers. If you have any questions at all after this talk, please feel free to reach out to me. email address, Twitter handle, both on the screen here. And with that, if there are any questions, I'm happy to take them.
Thank you so much, Kevin. Does anybody have any question? You can unmute yourself and ask.
Hey Kevin, I have one question. At the beginning, you said like there can be like hundreds of tables, we can have in our database. And right now we had an example of like a very small database size. It was really easy to like visualize. So what will be your strategy or recommendation when you are handling like 100+ databases, or like 100+ tables, or multiple database sources and stuff like that? Like
yeah,
how would you able to like figure out the, like this can be really helpful if it's like at a small stage, but I just wanted to know like what's your recommendation?
Sure. So the larger example is essentially following the same practices as I walked through in this, except with quite a bit more legwork, a bit more filling out your own notes. So essentially, take it from the top. Look at the biggest, meanest, largest table. Look at its relationships. Figure out that spider web of tables that connect together. Because even if you have hundreds of tables in a database, like the OLTP systems I work with at my day job, got a couple thousand tables in that database. But there are several different schemas, and even within a schema, there are sets of tables that connect together and other sets that are completely separate. So easiest way to understand it is a piece at a time. Pick a big table, look at the things around it, try to understand that subsection. Keep your notes, and then go pick the next table. Go understand the next subsection. See how things slowly build up. And there may be dozens of tables that you just don't even look at because they don't tie to anything else, or they don't relate to what you're really interested in. There are only a few hundred rows in them, or you start looking at it and all the data's from like 6-7 years ago. So that may simplify your problem a little bit. But yeah, the concept is still going to apply even if you have thousands of tables. It's just going to take you longer to understand. But start with the largest numbers because those are probably the most active tables. Those are probably the ones that people care about the most and probably have the most interesting insights. With the exception of log tables, audit tables, history tables that may not contain interesting information at the present day. Hopefully the names of the tables will tell you that quickly.
Yep, that answers my question. Thank you.
Sure. Any other questions?
Okay, Kevin, thank you so much. This was very insightful. I did learn a lot, and I'm very glad that you're able to make it today. Thank you, and thanks to everybody. Feel free to reach out, charlottebigroup@hotmail.com, or you can reach out to me on LinkedIn. My full name is there. If you look at the people attending this meeting, you see my full name. Unfortunately, I can't send you a chat. For some reason, it's not available. Brad is also one of the organizers, so please feel free to reach out to any one of us on LinkedIn or send an email. So that's it for today. We're not likely to have a meeting next month, but we'll keep you all informed. We'll send messages out when we have a plan in place. Okay? So that's it. Good night and enjoy the rest of your evening. Bye. Bye, Kevin.